Right, so in a previous video we looked at the generation of three-phase currents ISA, ISB, and ISC based on a torque and a speed command, and we looked at the machine model and all these kind of things. But what we want to do here is we want to look at how are those currents actually generated in a practical system. Like, how can you control those currents to give you the kind of behavior you want? So we're essentially going to add the last piece of the puzzle into this discussion of induction machine control. So, I guess a brief review of what we've done so far is, so far we've seen ISD and ISQ, and again, these came from the machine vehicle model, or whatever you want to call it. So this is ISD and this is ISQ, and this is, this is what we're trying to do today. We're trying to look at, or in this video, you have a current controller or control, whatever you want to call it, and the output of this current control should be VSD and VSQ. These are both references, and these references will go to a DQ to ABC frame transformation. So this will be DQ to ABC, and this angle here is the same row approximation, let's say, the same way we generated it before in the previous video. And so if you haven't seen that video, I'll link that in the description below, so you can actually refresh yourself on what it is that we're talking about here. And the outputs here will be VSA star, VSB star, VSC star, and they'll go to a PWM, pulse width modulation. And again, the power electronics is not really the focus of this material, so you'll have to kind of work on your own to really understand what PWM is and how it's used. And the outputs of these, usually they call them some modulating index, let's say MA, MB, and MC, and these three will go to inverter. So the inverter will generate the signals that we need based on the values of MA, MB, and MC. Now, this is the most common way that we approach this, but this is the story that we have, right? So this is all coming from the vehicle model. So I guess you can write some here, a vehicle model somewhere there, I guess. Probably didn't do a good job in drawing that, but essentially you'll have all of this coming from a vehicle model, something like that, and you'll have these currents, you'll have all of this stuff. And again, this is from a previous video where we've actually generated these currents. Well, they're reference currents or whatever you want to call them. And based on those, well, I guess they are references, so I should probably include the stars here as well. So based on these quantities, we will go through and we'll look at how can we generate, or how can we actually control the current and generate VSD and VSQ to give us the voltages we need. To do so, we have to go back to our equations for our for the induction machine. And again, just a warning, this is another one of those mathematically dense videos with a lot of equations and all that kind of stuff and manipulation, and it's just the nature of the thing we're trying to do. Anyhow, recall that d lambda s by dt is equal to Vs minus Rs Is, right? So this is one of the first equations we saw when discussing the induction machine. Okay, now we can rewrite lambda s as follows. So we can say d over dt of Lm 1 plus sigma s Is plus IR prime, and we can do that, and I guess this whole derivative applies to all of that, and this is Vs minus Rs Is. Okay, now we had an expression for IR prime. If you recall, we had IR prime in terms of IMR and Is, right? So we can make that substitution as well. And we can also simplify this derivative term a bit. So we can say Lm 1 plus sigma s dis by dt plus Lm d by dt IMR e to the j rho minus is over 1 plus sigma r. And this is exactly that substitution I was referring to. So this thing is actually, this thing is IR prime, right? We made this sort of relationship change that we did. Change of variables, if you want to call it that. Defined new variable, Vs minus Rs Is. Okay. Next, what we can do is we can simplify this. We can rearrange it. We can make things look a little more pleasing, I guess, if there is such a way to do so with such an equation. We'll say Lm over 1 plus sigma r and 1 plus sigma s, 1 plus sigma r minus 1 dis by dt plus Lm over 1 plus sigma r. Here we'll have dimr by dt plus j omega simr e to the j rho. And this is equal to Vs minus Rs Is. That doesn't look any simpler, but I assure you by the end of this video we will have something that looks simple and nice and neat. Otherwise we wouldn't really be here discussing this. What we'll do is we'll define something, we'll call it the total leakage factor, okay? So we have these leakage factors sigma. So let's define a total leakage sigma factor, and let's call it sigma, right? Just sigma. And sigma will be defined as 1 minus 1 over 1 plus sigma r times 1 plus sigma s, okay? This is what we're defining. So if we make this definition, then you can say that 1 plus sigma r or times 1 plus sigma s is equal to 1 over 1 minus sigma. Again, just rearranging the equation that I have there on the left side. And if I do that, and I apply this simplification to, or this, I guess, definition to this equation I have here. So I'll take this term here, and I can apply this, and I can plug it in there, and I can rearrange the whole equation, and I can simplify things. And I'll skip some steps here in this video because, again, if we don't, we'll be here forever. But the equation that you end up with is Lm 1 plus sigma s over Rs sigma dis by dt plus, this is the multiplication there, plus Lm 1 plus sigma s over Rs 1 minus sigma dimr by dt plus j omega. I think I used omega s, and we don't use omega s. We use omega for the frequency, right? So that's a mistake. I apologize for that. So we'll have j omega imr e to the j rho, and this is equal to 1 over Rs Vs minus Is. So we got rid of the Rs on the Is, and we sent it to the other side, and we divided the whole thing out, plus whatever other simplifications we have made based on the new substitutions that we, the new definitions and the new substitutions that we carry out. Now, let's go one step further, and let's define another thing. Let's define a time constant, tau s. So we had a rotor time constant. This is the stator time constant. So this is defined as Ls over Rs. Very straightforward. Now if I do this, I substitute this into the equation, and I make some additional simplifications, I'll end up with the following. I'll end up with sigma tau s dis by dt plus 1 minus sigma tau s dimr by dt plus j omega imr e to the j rho is equal to 1 over rs vs minus is. Now we know that vs and is can be expressed in terms of their d and q components. So, I mean, you can say, for instance, that vs is equal to vsd plus j vsq, and both of these multiplied e to the j rho, right? We know this is true, and we know the same thing is true for is, right? So if we do that, let's make those substitutions, and I'm not going to do that because, again, the equations will get really long, but I can make those substitutions into both vs and is, and then I can equate the real components and the imaginary components of the resulting equation, and you'll end up with two equations. If I actually did that here, it would take long and it would be very tedious for very little value. But the resulting equations that you get once you carry that process out, you'll get two equations. You'll get one equation that says sigma tau s disd by dt plus isd is equal to sigma tau s omega isq minus 1 minus sigma tau s dimr by dt plus 1 over rs vsd. This is one equation. And the second equation that you get will be similar. So it's sigma tau s, but it's for d isq by dt plus isq equals minus sigma tau s omega isd minus 1 minus sigma tau s omega imr plus 1 over rs vsq. Now, in this state, they don't really look very nice, I guess. But if you consider steady state, for instance, so these are two differential equations. I mean, these are, call this equation A and B. I don't want to call them 1 and 2 because in this entire chain of videos, we've had a certain numbering. And I don't want to break that numbering, I guess. So we'll call this A and B. So equation A is used for ISD, equation B is used for ISQ. You'll see that equation A relates ISD to VSD, and equation B relates ISQ to VSQ. But you'll also see that the equations are coupled. And they are coupled because this is ISQ, but this is ISD, and this is ISD, but this is ISQ. Now, this is not an issue because we have methods, and I'll show them in a second, we have methods by which we can decouple these equations through control implementation. Little tips and tricks that you can apply. But the important thing here is to look at now steady state. What do these equations look like in steady state? So in the steady state, derivative terms go to 0, and you can simplify the equation, and you'll get two equations. You'll get VSD is equal to RS ISD minus sigma 1 plus sigma s lm omega isq, and you'll get VSQ is equal to RS ISQ plus sigma times 1 plus sigma s lm omega ISD plus 1 minus sigma 1 plus sigma s lm omega imr, right? And imagine, well, I mean, not imagine, this is actually what we do in control. So we say that if ISD is equal to IMR's reference and ISQ is equal to ISQ reference, then you can replace these terms. So what's what? You can replace this ISQ, let's say, with ISQ star, and you can replace this ISD here with IMR star, right? And this IMR star should be the reference as well. So assuming perfect tracking and all that kind of stuff, IMR star. And then ISQ here is, of course, also ISQ star. So this is assuming steady state, perfect tracking. We have all the control implemented and everything's working perfectly. This is what we would end up with. Okay, so this is nice because now we have two equations, and these equations are very nice relative to what we started off with. And they basically express how the voltages VSD and VSQ are related to the currents ISD and ISQ. Now remember, IMR is actually equal to ISD, so it's an indirect sort of thing. And we introduced that to decouple the entire approach from the beginning. So the peak voltage that the PWM inverter will deliver then, we can call it VS hat, will be VSD squared plus VSQ squared, right? Because remember, this is essentially the DQ frame. You have a vector here, and this is going to be like VSD. So if this is VS, then this is VSD, and this is VSQ, right? And so the magnitude of this VS is going to be the square, the square root of the sum of the squares, right? Now, what else do we have? In terms of all of this, we can say that there are some things we can note. So this term here, well, I forgot to replace this one with IMR, right? This should also be IMR. This term here, this one, and this one, and then I'll underline this one with a different color. So the blue underlined terms are not very large, since sigma, sigma s, and rs are typically small values. The gray one, however, or sorry, the gray one, the red one, it's gray on my paper is why I said gray. The red one here is significant and will increase very quickly. Why? Because it's proportional to the speed, right? So it's related closely to the shaft speed. This is just something to note in terms of all of the relationships that we have here. Also, the reference IMR is decreased beyond the base speed, which is field weakening, in order to keep VSQ and therefore VS at a manageable value, right? So if you remember in the previous videos for the DC machine, we applied field weakening to increase the speed beyond a certain point. In this case, we're going to use IMR. In that case, we increased the speed by decreasing the field, or the flux K phi basically, through the field current. In this case, we're doing the same thing but using IMR to apply the field weakening. So now we can take a look at the overall modeling, let's say, of this. So using these equations that we have, the differential equations, I should say, A and B. So using the equations A and B, we can draw some block diagrams. Why don't we draw some block diagrams to understand how this control is implemented? Okay, so before we do that, why don't we take these equations, since we're going to be using them, and they are long equations, so I don't want to rewrite them. Usually I wouldn't be so lazy, but given the length of these equations, it's a bit of a waste of time for me to rewrite them again. So why don't we place them right here? And let's do the following. Why don't we how do we want to approach this? Why don't we, well actually we're not using these equations at all, so we don't need these. So we're using some parts of them and we're not. So let's start by doing this. Let's say U of D equals sigma tau S omega ISQ minus 1 minus sigma tau S DIMR by dt plus 1 over RS VSD. And we'll let another variable UQ equal minus sigma tau S omega ISD minus 1 minus sigma tau S omega IMR plus 1 over RS VSQ. Okay, now we have this. That means This means that the relationship between these two variables, let's say, so what is this variable here? This is UD, and this is ISD. The relationship between these two is 1 over sigma tau s s plus 1. And alternatively, the relationship between UQ and ISQ, so this is UQ and ISQ, is similar. Well, it's actually the same. This is 1 over sigma tau s s plus 1. So if you want to regulate these, then you can make your control loops look something like this. You can have a signal comes in, feedback goes to a compensator. This is your compensator. This is the output of the compensator. This is the plant. And so we can say that this looks something like this. And so ISD star is here. ISD actual is there. UD is the output of your compensator. Let's call this KDS. And inside here you have your 1 over sigma tau s s plus 1. So this is for the D axis. And then for the Q axis, you can do the exact same thing. And I guess we can label this technically as ED. So that's the error associated with the D axis. And you can do the exact same thing for the Q axis. And we'll do it just for the sake of completeness here. And this is KQ, let's say, S. And this is 1 over sigma tau s s plus 1. And the output of that will be fed back here. And this is ISQ star EQ UQ. Right. Now, in a case like this, because we applied the DQ frame transformation, we can let these two compensators, KD and KQ, be PI compensators. Because we're basically tracking a DC reference, because we say our frame is in line or at the same speed as the as whatever phasors we're trying to track. So let's say that the two, let's say KD equals KQ equals KI, right? And I mean, I should say that S, right? These are functions. So KD of S equals KQ of S equals, let's call it KI of S. And let this be some KP plus KI over S. Okay? Okay. Now what we can do is we can cancel the pole of the plant with the 0 of the compensator, which is a technique, it's a very common technique. So the loop gain, LS, is equal to KP S plus KI over KP divided by sigma tau S, S plus 1 over sigma tau S times S, right? So we say if Ki over Kp is equal to 1 over sigma tau S, then the loop gain Ls is equal to 1 over sigma tau S over Kp times S. So you're left with an integrator basically with some gain, and that gain is controlled by Kp, tau S, and sigma. Tau S and sigma aren't really under our control, but Kp is, so we control the time constant with our proportional constant. Okay, so then you can write the overall closed loop transfer function as you wish, and you end up with the generic 1 over tau I S plus 1. So if you want, then we can say that G of S is equal to Ls over Ls plus 1. Maybe we can write that a little bit neater. Ls plus 1. And I guess you can say that in both cases, you can say that ISD over ISD star is equal to 1 over tau I S plus 1. and ISQ over ISQ star is equal to 1 over tau IS plus 1. And we say that tau I, in this case, is equal to sigma tau S over Kp. So based on your time constant, you can set your Kp. Based on Kp, you can determine your Ki, and so on. So maybe we can just summarize that right here. And we can say that Kp is equal to sigma tau S over tau I, and Ki is equal to 1 over tau I. So you set a time constant according to your requirements, and you end up having everything you need to solve for your control parameters. Now, the last thing we're going to do here is we're going to look at how do we implement this control. How do we implement the little trick that I told you about to decouple the currents from one another? And how do we finally finish the entire control chain? It looks something like this. So you have ISD going into some little summation block. And these, I should say, this is one of the more complicated. It's not complicated because it's hard. There's just a lot of things going in a lot of different directions. So there are a fair bit of blocks and such to draw here, but we'll do our best to make it as neat as possible. So you have some block here. You'll have off. So maybe we just draw this here. One block here. This is a multiplication block. We'll have another block here, like so. And then we have another sort of chain and another set of blocks here, like this. And you'll have these summation blocks here again. You'll have another compensator here. I guess that's a bit of a spoiler because I didn't really say what they are yet, but that's okay. And you'll have another multiplication block here, go into another function of some sort here, and the output on this side, same, and then this giant, let's say DQ to ABC frame. The outputs of these are voltages. So let's start filling some stuff in. DQ, I thought we erased that, never mind. DQ to ABC. This is going to be VSA star, VB star, VC star. This is RS, and this is RS. This here is VSD. And again, these are based off of the differential equation. So this is not, I'm not just pulling these out of like thin air. These are, I mean, although it might appear so, but these are modeled by the differential equations that we derived, right? And this is that little trick I was telling you about that we can use to decouple the control, basically. By adding and subtracting, well, adding from one side and subtracting on the other, you can basically use what they call feed forward in order to nullify the effect of one variable on the other. So in the middle here we have omega, and omega comes in like this, and omega multiplies with both of these. So why don't we call this omega? And then omega also goes down like this and multiplies. I'm going to run out of space, but that's okay. We can scroll up here. And omega is going to multiply here with a current. And, well, that's going to be confusing, so let's do this. This, if this wasn't confusing enough, right? This subtracted, this is subtracted there. So this is ISD star. This is ISD actual, right? So this is the actual variable that you feed back. And while feeding that back, you're also going to feed that through here, right? And these are going to be sigma tau s and sigma tau s. And I'm going to do the same thing at the bottom. I'm going to take this feedback signal and I'm going to apply it to this block as well. And this is ISQ star, and that's subtraction there. And what's inside here? This is KIS, this is KIS. What else do we have? We have here 1 minus sigma tau s, and here we have 1 minus sigma tau s. And this thing, maybe we can draw it this, just so we can have everything fitting properly. And this is dimr by dt, and this comes from the flux model. It's optional. It's a feed forward that you don't need, but these feed forwards here you do need. They're highly recommended to use. And what are we missing still? We're missing, we're missing just this last couple of currents here. So we have ISQ, you probably knew that by now. And then here we have IMR, and of course we have to have rho coming in here as well. So you can't forget about that. And we can probably add a little note saying that this thing and this thing are from flux model. So that flux machine model that we looked at before, and this is where those come from. I just want to make sure we have everything, and it seems like we do. So, what's the little trick thing that I was saying? Well, maybe I guess one last thing we can say is here, and you can say to PWM. To PWM. So all of this goes to the PWM. So the thing to note is, in these differential equations that we had here, in these differential equations, you'll notice, in the differential equations, you'll notice you had an ISQ and the ISD. So if this here depends on sigma tau s omega ISQ, then why don't I just subtract from this chain this quantity? And then I add this quantity to this chain so as to eliminate the effect. So that's why you'll notice on the top, you subtract this. At the bottom, you add it to nullify the effect. And so all of this is then generated based on the machine model and the flux model, whatever you want to call it, and it's fed to the PWM. The gating pulses for the inverter are produced by, let's say, some sine triangle intercept method or PWM method. The details of that, again, are outside the scope of the material we're studying here. So if you're interested in that, you can leave a comment below, and I'm more than happy to discuss it. But in terms of formal education of that, it's not really the scope of what we're trying to do here. So again, this was one of those really dense videos, and I warned you at the beginning that it would be so. So a lot of rearranging, a lot of mathematical derivations, but essentially what we did is we established what this current controller should look like. So we know what the vehicle model looks like, we know what the current controller looks like, we know what the DQ at alpha beta, DQ at ABC looks like, and we don't really care about the PWM. So we have a complete representation now of what it is we're trying to do here. So to go through all these steps, it's tedious, yes, but it was obviously necessary for the purpose of the control that we're doing here. After running through all of this, we arrive at a model that looks, we arrived at some control loops. Before that, we calculated what the gains should be for the PI compensators for these control loops based on this pole zero cancellation method, which is a well-known control technique. Sorry, just had a bit of a glitch there because for some reason this program seems to be glitching. But then we arrived at some final block diagram, which for whatever reason does not appear to be displaying on the screen because I guess OneNote has become overloaded. There it is. Part of it at least. And then we arrived at this thing. So this thing you would implement in your simulation. of course, this DQ to ABC you would implement based on whatever techniques you just decide to use. And to generate ISD and ISQ, you would use the previous machine model. So I know this was a lot, but I hope this was helpful. If you have any questions, please leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.